What we're looking at specifically is inclusions in molten steel. Inclusions are hard ceramic particles and they decrease our fatigue limit and increase the likelihood of failure. So what we're looking at specifically with Gerdau at their Monroe mill is calcium aluminates and calcium sulfides. So these inclusions start to form in the tun dish, stopper rod, and mold area. What we see is the inclusions will come down out of the tun dish through the stopper rod and they'll start to clog on the stopper rod, specifically calcium sulfides. And this clogging is an issue because our stopper rod can oscillate to maintain a fluid flow to the mold, but it can only increase until like 3 millimeters. And so sometimes they get buildup of calcium sulfide so great that they can no longer maintain a consistent fluid flow and they have to tail out. And so that's really what we're studying to see if we can model this more correctly so that they don't have to tail out as often and lose money in production.
And so what we found in literature research and some information we got from our sponsor is that we can model this comparing calcium parts per million to aluminum parts per million. And if we have too little calcium, that's when we form calcium aluminates, which is in that yellow region right here. And if we have too much calcium, we form calcium sulfides, that's this blue region right here. But if we have the right amount of calcium at the right amount of aluminum, we have this purple region, which is our liquid window curve, where we will no longer have the issues that we explained earlier in the tun dish.
So how we went about proving that our curves are correct is we asked Gerdau for some historical data. So that's this graph right here. The red points are bad heats that Gerdau had that had too many inclusions, so they fall below the line, which is correct. And then we have green points, which are good heats, which had not as many inclusions, and they fall in between the liquid spindle curves, so it verifies that our curves are being produced correctly. This is what a typical curve looks like, so that they have various software levels depending on what heat they're melting. And then further, to test our own steel in our foundry, we made a DOE with points of chemistries that we wanted to aim and target to hit. Gerdau uses all scrap metal, and by creating these liquidous window curves, it allows them to buy a wider range of elemental compositions because they can adjust it throughout our code and know what points to hit throughout the curve. We also will be giving them our code, which allows them to run any heats if they run into any problems. And that's our project.